Convenient. Others. Okay, so last time we established Mellin-Barnes integral representation of Gauss hypergeometric function, and the summation of the residues of certain gamma factor. So Mellin-Barnes representation for so that the one an argument this admits minus s minus z to the power s divided by gamma function of small gamma plus s. That is it. Maybe I use other yellow one can be better. So the integration path C, where it is, it has poles, oh, it's also poles along poles of this this factor as s equals as positive integers, isn't that? All positive integers. So and we want to gather the residues of this expression. These negative integers, first order poles. So CMOS and so 0 positive side, 1, 2, and so on. And this factor has poles along minus alpha, minus 1, minus beta, minus, and so on. So if we take C minus I infinity, C plus I infinity, this integration path as a path that goes from imaginary part minus infinity to imaginary part plus infinity, that divides these two groups of poles of this factor. So in this manner, so according to setting formula, we see that this integrand function decreases, exponentially decreases. So this integral convergent, and even we can deform the integration path in such a manner that it shrinks somehow into this kind of 0, 1, 2, and so on, yeah. So in this manner we how shall I? Okay, okay. Okay, so in this manner, I recall shortly, briefly, the procedure. Whether this one writes well. It seems to write better. So let us consider the poles of this factor. The important thing is that something you recall, S equals n, gamma minus S, ds, it's n factorial minus 1, n plus 1. So gamma, in fact, this is residue of t, say t equals minus s, okay, and t equals minus m, gamma t, dt minus. So that is say minus m, okay, usual, so residue. And this one is minus 1, we have minus 1 here, and minus 1, m factorial, minus 1 to the power m. That is say, the sign changes. Sign changes once. One sign changes, and so this is negative direction. That is say, so in fact it is minus residue. What we were counting here. So it is minus residue is minus this one. That is say itself. Okay. So after using this formula, you simply gather the residues. Remaining factors are holomorphic. So suppose that alpha, beta, really positive, say rational numbers, and that is say this integral becomes residues at these positive integer points. That is say gamma. The result is gamma alpha, gamma beta times. So this part, remaining part is holomorphic. So replace S by M. That's all. What you shall do. Gamma plus M, and then finally and minus 1 minus Z to the power M. Yes. And this one, this residue. Residue is minus 1 to the power m factorial. Okay, you see? And you see that minus m to the power m appears twice. That is say, it's really turned into z to the m factorial, z to the power m over m factorial. Yeah, that's it. So that is, and this expression, this kind of thing, yeah, this kind of rational expression was Pohama symbol. So we see that it is really gives us series expression of Gauss hypergeometric function at an open unit disk. So this is the one say in terms of Gauss hypergeometric function, hypergeometric differential equation. So where is it? The solution space of Gauss hypergeometric equation has dimension dimension 2 over complex field, complex number field. So I wrote it. Z, where is it? Minus theta z. Yes. Where is it? No. Yes. Minus theta z, comma minus 1. That was theta z is z dz. The second solution, the first solution is this one, and the second one was z to the power. So U solution space is linear combination C1 F alpha beta gamma F, and you shift these parameters by 1 minus gamma, isn't it? By 1 minus gamma, and so it gets z to the power 1 minus gamma F beta plus 1 minus gamma. So this shifting so we have the second solution. That is monotony that ramifies around z equals 0. Yeah. So this one is this expression. This expression is a holomorphic function defined by this kind of series. Where is it? Yeah, this kind of series that you simply replace alpha beta gamma by these numbers, by these parameters. Okay, so now let us express this this function in terms of Mellin boundary integral. Mellin balance integral representation of this function, of this second function. So, in fact, it can be done very simple way in modifying this first Mellin boundary integral representation. So I can use these two So the answer is the following. Yes. So the answer is so this function, the Mellin balance of second function, if maybe I denoted by f2 somewhere. This one f1, or I don't remember. Yeah, so maybe there's some constant factor may be different. Is equals also a summation of residues e to the power minus pi I 1 minus gamma integration the same. Maybe I need yeah, okay, let us see. Over, so this factor, this factor is different. So these two factors, yeah, are the same as the previous one. The new ds, yeah. So new fact appears here. So let us compare these two integral representations. In two integral representation, two integral representations. So this one and this one, yeah. So the difference is this factor somehow come down, and this factor goes up. So how, in fact, let us denote this function entire means this entire function by yeah, everything included, everything, yeah, including the constant factor. The constant factor. So let me write down simply this, everything inside C plus I infinity, and this expression by let us denote this expression. I forgot to write ds. ds, yeah, and so let me denote by gs, and this expression, yeah, as a meromorphic function in S. For and denote this one by HS, say, I can write it this manner, that everything C plus I infinity. This one is entire question HS. Okay, and yes. So the difference, the main difference is here. So we recall here the Euler reflection formula. Formula for gamma function, that is, say, gamma S gamma 1 minus S equals pi over sine pi s. This is somehow well known. It is not so easy to prove it. There are different ways to prove it, but the important thing is that, so for example, from this you see that S has poles, first order poles at S equals 0, minus 1, and so on. And here this one has poles of 1, 2, 3, and so on. So this function has first order poles at every integer point, and so this agrees, of course, with this expression, this meromorphic function. Yeah? Pi over sine pi s. Yeah. That is, say, so, and maybe HS, yeah. So gamma alpha plus S, okay, GS times something, constant times something, yeah, constant and yeah, this function appears constant. Wait a minute. Maybe it's better to gamma gamma alpha plus S, gamma beta plus S. This is, so what is the main part of GS function, yeah, GS function, times Vs, and get some meromorphic function, yeah. There is a meromorphic function, and meromorphic, there exists meromorphic periodic function, periodic meromorphic function. Periodic, that phi of S, phi of S plus 1 equals phi S itself. Now, the period 1 is period 1 equals, so gamma gamma 1 minus gamma plus S divided by gamma 1 plus S. So phi S we can calculate very easily, isn't it? So simply, these are the same. So this one is some HS factor of HS. Okay. I forgot to write S here. Yeah. No. It is really constant. Yes. It's really constant. Yeah. It's really constant. Yes. So from HS as a constant times it is okay. I can write the constant times non-zero constant times HS is this one, non-zero constant times GS equals this. Huh? So the essential part of this meromorphic function, where you shall deal with the residues, concentrated here. And Vs, you can calculate very easily this meromorphic function Vs as gamma of 1 minus gamma plus S divided by gamma so what happens? Sorry. Times gamma 1 minus gamma plus s times gamma plus s, isn't it? Yes, gamma 1 plus s and gamma 1 minus 1 plus s times gamma minus s. So in making use of this Euler reflection formula, you immediately see that this is equal to sine pi of gamma plus, wait a minute, denominator, sine pi gamma plus s over pi times pi, I think that minus s, yes. Instead of s, I put s. And it is pi gamma plus s and pi over sine pi s. Sine pi s. Okay? Yeah, nothing. Yes, everything right. Yes. So this is Morphic function with period 1. Is period 1, isn't it? So the in other words, so what I want to say is the following: this multiplication has quite an important role in it can be generalized to more higher order operators and many variables and so on. So the point is that this integral really satisfies this. You see, in making use of this periodicity, in making use of this periodic periodicity of this phi s factor function, the fact that this integral this fact entails the fact that integration of c minus infinity hs ds satisfies. So let me write two integrals. ds, and maybe instead of writing hs, I can write something gs times phi s up to constant, some constant factor. Okay, so this is constant times hs. And so the point is that both satisfy the same differential equation. Or, in other words, GS satisfies GS equals, wait a minute, so GS, yeah, GS are included this factor. So, differential equation that comes from the difference equation. Valid for coefficients. So let me not GS. Okay. I can write GS also. GS. So difference equation. In fact, we saw that this. Where is it? Yeah. This differential. Where is the differential equation? I raise it. I see. Yeah. Okay. Yeah, this differential equation. Yeah, this differential equation has been established by comparing coefficients of expressed in gamma function. So, yeah, that is, say, if I apply this operator, say theta z first apply this one. So then by Fubini theorem we can change the order of integration and differentiation, derivative, and I differentiate this expression. Then what happens? This is it will give rise to z to the power s. It will be gs will be so s times s plus gamma minus 1. That's all. Yeah, times gs. And then on the other side, on the other hand, we have this. So if I apply this operator, theta z plus beta, then I will have z times s plus alpha times s plus beta, and that times gs. Okay. So so z times gs. Z times gs is minus, is not is z to the power s plus 1, gs plus 1. I want to express it by means of yeah, s plus 1, and s plus 1 will change everything here. Yeah, let me do it. So we compare that times so what is GS plus 1? GS plus 1. What is GS plus 1? GS plus 1 is gamma alpha plus S plus 1 gamma plus S plus 1 minus 1, isn't it? Times minus Z S plus 1. I see that, but this is, of course, alpha plus S times beta plus S divided by gamma plus S divided by minus S. Times this. So this entire expression, so minus S minus minus S minus 1. So another what is the ratio between how I recover gamma minus S? Gamma minus S minus 1 minus S minus 1 equals gamma minus S, isn't it? That is, say minus 1 minus 1. Okay, that's okay. So and minus Z power so and gamma factors these times minus Z to the power S. This is exactly G of S times minus Z. Okay. So this relation, S plus 1. In fact, if I replace it S G plus S so simply I want to say that this GS function satisfies recurrence equation, the difference, a kind of difference equation. GS plus 1 is expressed by another GS times this one. Yeah? So if this recurrence relation is satisfied, yeah, and of course if you multiply by Fs plus 1, Vs plus 1 of Vs, so Hs plus 1 equals the same factor times Hs. Hs, that is a Gs plus 1 times Vs plus 1. because phi is periodic function. So that is say, the solution to the differential equation admits as a if you express in terms of many members integral, certain multiplication by a periodic function plus 1. Yeah, phi s equals phi s plus 1. So you have other choices, of course. Then, in any case, other choice will be again the summation of linear combination of these integrals. These integrals you have. In fact, this, yeah. So later, it will be related to homology. Homology basis choice. Oh, maybe you have. I have no need to. So multiply by thanks to the multiplication by phi s, maybe phi s. We got new series expansion that has monotonic behavior, branching behavior at 0. Z to the power 1 minus com. New one. You not give one, new one. So in this way, you get production say production of new solutions. So to the moment, two new solutions. To the moment, it is only one function. Of the same hypergeometric differential equation. Maybe to the moment it's only one. It's so if we understand a solution, each solution somehow correspond to homology basis, then it will you will see that it is this procedure can be interpreted in terms of taking into account of new homological cycle. Yeah, this one is quite important, and it is. I simply hinted now. So remember that this one was 0, 1 yz, isn't it? This one was 1 over z to the infinity other. I think so. Any case, yes. 1 over that. Yeah. So this one was correspond to another cycle, eh? This one corresponds to one cycle, and this one other cycle. Yeah. So this picture, in fact, can be generalized in a very far, more generalized setting in toric geometry. That is the reason why I'm giving this lecture. So, okay, we got the second. Now we see that more or less that both solutions of this, both hypergeometric functions admit Marin bound integral representation. Yeah, more or less somehow unified manner, and the essential part can be controlled by this periodic function multiplication. Yeah. So now we want to discuss the monodromy. Monodromy. That's somehow I denoted another way. Yeah. Yeah. Sorry, in the note I made a different notation. What is this? Yeah, maybe, sorry. So, yes, further I shall use not, yeah, sorry, that, not this one, that's simply this one as GS. In fact, what I've written here, yes, GS, so that is, say, GS times GS minus z to the power s is lacking. Minus z to the power s is lacking. So okay, so let us denote this one. Right, alpha plus s, beta plus s, gamma minus s, power s. This one is GS without constant factor, multiplication factor. And the other one, HS, is, say, the Merrill-Morris function that I interchanged. So HS equals GS times is sine pi that is this one, yes. In other words, let us consider these kind of basis of solutions. Of the hypergeometric equation, yeah, this one. Both integral representations satisfy the same differential equation. And now we want to calculate the monodromy or analytic continuation of Hypergeometric functions from the neighborhood of 0 to the neighborhood of infinity. So this is a global problem. So to pursue the global behavior of this. And to do this, we essentially use this let us recall again this picture, how so gamma this factor. So first one, GS. First consider GS, okay? HS has other poles, other types of poles, but first consider GS. That it has minus alpha, minus 1, minus beta, minus 1, and so on, okay? These are the other poles. And it is divided in two parts. And the integration passes like this. And first, we got series expansion around that equals 0 in the neighborhood of 0, and gathering these residues. In fact, it corresponds to the fact that we gather the residue as z positive, that is z to the power m something, wasn't it? That corresponds to that is say convergent in z in a neighborhood of z equals 0, positive. And now we do something. We deform the integration path. That is crucial point, quite crucial point of all this story. To gather residues that are located on the left-hand side of this separating integration path as an initial integration path. This is the same. So then the result will be gathering of these residues. That is say, so let me yeah, let me denote by G1S, G1Z equals minus, yeah, because this is minus negative direction. So okay, of summation of residue of GS. And then for so S convergent in then after this contour throw, I coined this procedure main imbalance contour throw. So the first one is G1, capital G1 G1Z series is obtained as integration along this path. And the second one would be obtained as integration along this. That is nothing but summation of residues at minus alpha. So that is A equals now positive because the residue, so direction is positive. Yeah, so plus 1. This is minus 1. That is negative. Yeah, negative direction. Yeah, this is negative direction. And this now as we gather residues of these poles, first order poles, anew, in positive direction, so that to get this one, so anew positive integers, but residues S equals minus alpha minus m of GS plus residue of S equals minus beta minus m. Yeah. That's it. So this one, this is convergent. These are series. So what is this? This is something like 1 over z minus alpha. Z minus alpha. With you put z minus alpha z to the power m minus m, and something. This is the series that you get as in gathering these residues. Okay, that is convergent in z equals infinity. Z near infinity. Both of them. Okay, so in a similar manner, I can do it for the function HS also. HS function, meromorphic function, has poles where it has poles. It has poles. It has poles on a positive. Minus S so plus m minus gamma plus m, yes, m positive integers, positive non-negative integers, poles. Okay. So to the moment, for the simplicity, let us imagine that gamma is smaller than 1, some rational number, 1 over 2, 1 over 3, and so on. Not 2, but so HS function has poles somewhere here, okay? So HS function, HS has poles at poles of HS. So on the left half, it has the same. Yeah, it has as poles at minus beta minus m. On the positive side, it is 1 minus gamma plus m. Yes. So m runs from 0 to. So if you want, you can put some number, one half or 1/3, some number. So this is the first one is 1 minus gamma. 1 minus gamma plus 1, 1 minus gamma plus 2, and so on. I have other poles. No, it continues. Which one? Gamma plus m. M, yes, m. So m equals 0, m equals 1, m equals 2, and so on. These are poles of this HS function. You see? So if I denote by, say, I write here, G2 summation of residues, minus, it is also minus times residues of S equals 1 minus gamma plus m. Okay, so it's shifted. HS. It is exactly this one, in fact. So up to constant multiplication. And then I do the same thing. So it is new after contour throw I gather residues S equals minus alpha minus m of HS and residues of minus m minus beta minus m. S equals minus beta minus m of Merrill-Park function HS. The structure is the same. And this one also convergent in here. So in total, in summary, we got the following formula. Following formula, G1, G2, the analytic continuation G1 and G2. So GJZ, the Jacob 1 and 2, has some and BM this kind of J equals 1 and 2. But the right hand side, this one is also, this one is also, it must also be a solution to hypergeometric equation, isn't it? It was also, that is say, it is admitted by some, there exists some constants, C1 prime C equation and a solution that is say dimension 2 2 over C, and that is say that admits H so let me denote by G infinity, to introduce new basis of the solution space. Let me denote by, so there is a solution that behaves like 1 over z to the alpha times holomorphic in 1 over z, isn't it? And there's another one that is 1 over z beta holomorphic in 1 over z. There are two types of solutions. Let me denote it this one solution. So yes, okay. Let us write down more precisely this solution. In view of the fact that the differential operator was z times isn't it? So we see that near z equals infinity, this part you can somehow this operator is dominant somehow. And you can find a series expansion of the form like this, and with dominant term 1 over z to the power alpha. Let us denote this solution by G alpha, G infinity z alpha. Maybe I begin from 1 plus some homomorphic 1 over z. Let us fix 1. And the second one, it also begins from homomorphic 1 over z. Higher order terms. Let us denote this solution G infinity z beta. And you see that the monodromy of the solution space, these solutions around 1 over z equals 0 is very simple. If alpha, beta, so what I will say, around, if 1 over z goes to e to the 2 pi I 1 over z, or no, z, how do I regularize? Yes, I regularize in this manner. Yes, to e to the 2 pi I 1 over z. 1 over z I consider as a variable, new variable, kind of 1 over w. Okay, and then this operator becomes minus theta w plus alpha w plus beta minus w times this is the expression of this differential operator in a new coordinate. New other atlas. So this is W, okay. Then by this monodromy action, loop, analytic continuation along the loop that turns around W equals 0 in a positive manner. That is say 1 over that. I think that so this must be negative term around. Simplest way to understand is that z equals 0, 1, and positive term is like this around these points, but so this one, you shall look at this infinity on the left hand side, left. Always, sorry. Positive term, positive term, to consider positive term around z equals something, z equals alpha. You must move around in looking alpha on your left hand side. That is like this. That is this is this kind of loop. In fact, it again corresponds to the fact that loop around 0 and 1 and infinity, the composition of 3 loops will be identity, the trivial element and the fundamental group of P1 minus 3 points. Yeah, this is another way to see it. Okay, so let us fix in this manner these two solutions and consider the monodromy around this path. Then what happens? What happens is this, and I have this, and G infinity Z alpha G infinity Z beta along this L infinity, the result. So I don't know this L infinity, or it is homotopic to this. So the class is the same. Yeah, homotopic class is the same. Small loop around infinity, around z equals infinity. No, small term around w equals 0. It will give you very simple monodromy Z alpha. Yes. Yeah, it's diagonal matrix. E to the power E alpha is. I always denote this. Lambda, real number, number, yeah, it is notation. Sorry. Notation. That is e to the power 2 pi I alpha. Because I can write many times this expression. So times, okay, let us know by G infinity times G infinity. This is a diagonal. So monodromy L infinity or I can write down H infinity notation is a diagonal matrix E alpha, E beta with respect to the basis say G I don't know this G infinity, yeah. These two special solutions. This vector, say, monodromy is a 2 times 2 matrix that acts on these functions. No, two-dimensional vector space. Whereas the definition, it is the definition. And so this monodromy is expressed in terms of a diagonal matrix. for a very special choice of basis. Now, our question is how to relate this function, yeah. Okay, the question is the following. So question, how to, shall we represent, how shall we get them, how can we get the monodromy representation that is a homomorphism from space of, say, solution space as an action of, say, I have L1 loop, I have loop, and this will give you analytic continuation along this loop of, say, function G1, G2. So G1, G2, G1, yes, G1, I introduced here, G1 was this one. G1 was this one. Summation of residues along these positive integers. That is, say, convergent in that small z. And also I had G2, where G2, local expression of G2, this one, yes. This is convergent in here, this one also. Because it is set to the power, positive power. Series in positive power, it is something like z to the power m plus 1 minus gamma bm, something like this. It is a positive power and it is convergent in z equals around z equals 0. It is local expression. And now the question is to get global monodromy. You see that? Get the global monodromy representation. In terms of, so G1, G2, that was, these were solutions, series convergent in small z. And consider the analytic continuation along every, so every kind of loop. So say something at z0, we begin dependent convergence. So for series G1, G2, both of them are convergent here. I began here, and consider analytic continuation. This way can be, or in fact any kind of loop. No, it can be any loop. So what is fundamental group? Fundamental group? Fundamental group is so group generated by these loops up to homotopy equivalence. Up to homotopy equivalence, okay? So, of course, we can consider this kind of loop also. Negative. Yeah. So, but this is, if I denote it, this one by this positive term L0 class, and then this one will be 0 L0 minus inverse. The class of this loop would be this. That is, say, it is equals here really in pi 1. Because the composition of two loops will give you a trivial loop. Huh? Let us say this. So we can consider also negative terms also. Negative terms also. So the expression of this as certain moment, maybe you weren't here. So Anania posed question why these are two generated by two loops, and general expression of this L loop is something like this. They're generated by only two L infinity, L0, L1 infinity equals identity, trivial in pi 1, yes. If you turn all the identity or okay, identity if you want. So L infinity can be expressed by means of L0 and L1. That is, say, this loop has L0 times A0, L1, A1, L0, A2, L1, A3, etc. And A0, all these numbers are integer, negative. The negative can be also. This is a general representation of this loop. For every loop, L, there exists sequences of integers such that L is homotopic, equivalent to this kind of expression. Okay? So to get this homomorphism, yes. That is, say, if I compose two loops, L1 and L2, I get two matrices. Okay, I write it. I write some matrix A, B, C, D. Today it's not so important, but sometimes. Okay, A, B, C, D, some matrix, yeah. ABCD in general linear group rank 2. So the question is to and by the one thing that we can see immediately is the following, that G1 was like this. G1 was G1 was really a holomorphic function along z equals 0. G2 is something like z to the power I minus gamma times holomorphic function. Holomorphic function in z. That is, say, G1, G2, the monodromy representation analytic continuation along a loop along z equals 0, then it is extremely simple to, that is, say, A0 as a loop around loop that is homotopical equivalent to z equals e to the power I theta epsilon times epsilon small theta 0 to pi. One term. Then L0, the analytic continuation along L would be L0, L0, yeah, L0, okay, L0. Would be simply G1 does not change because it's holomorphic. No, first I write simply like this, G1, and G2 will be multiplied by e to the power, so you imagine that z e to the z changes into z to the power 2 pi I, and you consider 1 to the 1 minus gamma, isn't that? So the result is e to the power 2 pi I, or if I use 1 minus gamma times G2, the initial value, I start from the same value. In fact, this is the same thing as to say that G1 e to the power 2 pi I z, G2 e to 2 pi I z. This is the meaning of notation. Then we get this, so the monodromy matrix will be diagonal 0, 1, 0, e to the power minus gamma. Okay, so this is G1, G2. So with respect to this basis, G1, G2, the monodromy representation is very, very simple at 0. With respect to this basis. And the situation is quite similar, where is it? At infinity. at infinity for another basis. For another basis that I denote by G infinity. G infinity, I erased. Yeah, maybe I erased, yeah. The situation was similar. Here I have. This one. So L infinity, I have L infinity G infinity alpha. Yeah, maybe for the sake of simplicity, G infinity equals this diagonal expression. This is one basis that has been chosen. Basis basis near z equals infinity. This is the basis near z equals 0. Now these are different bases, but they are the basis over C of the same vector space. That is, there must be a matrix, base change matrix. There must be a base change matrix. That is, say, we have base change matrix that connect these two bases that I denote by P. That is, say, G1Z okay, G infinity. Now that I denote by G infinity. Yeah. There is a base change matrix, and if you calculate able to solve this problem. To solve this problem, global representation, monodromy representation, it is enough to calculate the monodromy representation. So, okay, the global monodromy representation can be obtained if we know, if we get P, this connection matrix, basis change matrix. Okay, the story is like this. We have, so around 0, this is very simple. Where is it? Yeah, this one, yeah. Around 0, we have this diagonal matrix. Of course, it's gamma. I shall say that it is not integer, like this. Such kind of condition I need to impose. No resonant condition. non-resonant condition, but yeah. So on 0 I have this L0. And monetary matrix like this. On the infinity, this. But, so I need to connect the basis that has been obtained in a unit circle, open unit circle, to with the basis at infinity. So here I have and then L1 would be L1, so this will be obtained by means of this relation. No, this relation. L1 is simply L0. That's it. Classes homotopically equivalent. These classes. So it's enough to calculate two. Now the whole story, our task is reduced to the calculation of this connection matrix. This is P somehow, connection or base changes matrix. Or it is the connection matrix. Okay. So next lecture I will explain how to the concrete expression of this connection matrix in terms of gamma functions with quite intriguing structure. P itself has some structure, yeah, that we want to generalize in other cases. So, and everything shall be done in terms of this Marin boundary intervals. Yeah. Okay. So let us stop.